Hello and welcome to this module, which is about data dependencies and how they limit the available parallelism in for loops. All the examples will be done through OpenMP loops, but they can be applied to any kind of parallel loops. Okay, let's look at an example. Here we have a couple of statements which have some dependencies. First of all, there is a data dependence, also called a read after write dependence, between these two array elements. Actually, there is dependency between these two elements as well. So the sum variable is used in the first statement. You produce a data value, and this data value is used in the second one. This means that it's not possible to reorder these two statements. You can't, in particular, you can't execute them in parallel. This is called a true data dependence. This example shows a true data dependence as manifested in a loop carried dependence. The loop here, which is a loop that goes from I equals 1 to n minus 1, reads a data element in the previous iterations produced by the previous iteration, and it produces a data value for the current iteration. This means that these iterations cannot be executed in cannot be executed in any arbitrary order, so they have to be executed in the order as specified by this sequential for loop. It's shown here below with the two sort of iterations. You have iterations I equals 1, which produces data value here, and that is used in the next iteration. So it becomes clearly visible when you lay out the iterations in this way. This is a loop carried dependence, and this loop cannot, without rewriting, be parallelized with OpenMP or any other parallelism model here. So how can we detect dependencies? Well, we need to analyze how each variable is used within a loop iteration. Is the variable only read and never written? Fine, there are no dependencies. However, for each variable written, can there be any accesses in other iterations than the current? If so, there are dependencies. There is a simple rule of thumb which you can use to analyze a loop to find out if there are no dependencies or if it can be parallelized. If all assignments to share data are to arrays, then that's a good sign. And also, if each element of the array is assigned by at most one iteration, that's even better. But that is not enough. Final thing is that no iteration that is read reads elements assigned by any other iteration. Let's have a look at a few loops and see if we can apply these rules and find out if the loops are parallel or not. Here's the first example. It's a loop that goes from I equals 1 to n minus 1. It goes in steps by 2. So I is updated by 2 every step. Okay, first rule is the loop is the stores. Are the stores going to array elements? Yes. Are they updated by at most one iteration? Yes. This is the first two criteria. Secondly, is any element read updated is read by any other iteration? At first it looks like it because we access array element I minus 1. But then if we observe that we go in steps by 2, we actually see that I minus 1 is never written by any other iteration. Therefore, this loop can be parallelized. Yes, this is parallel. Second example here goes from I equals 0 to n over 2 minus 1. First rule of thumb, array element is written, yes. Is it written only by one iteration? Yes. Second, finally, can any element being read by another iteration? In this case, this also holds that there cannot be any reads by another iteration written by another iteration, because we read here I plus n over 2, and since the iteration goes to n over 2 minus 1, there is no overlap between these two regions. So yes, this is also a parallel loop. Third example here, same kind of same loop body, exactly the same loop body. Now instead we go to n over 2 inclusive in the loop iterations. This means that there is actually an overlap of I equals 0, because then you have n over 2 here, and also to I equals n over 2, because then you have the same array element being read and written. So no, this cannot be parallelized unless we take care of this borderline case. Final example. Sorry, I'm going to remove this one. Final example here. This loop uses array index elements going from I equals 0 to n minus 1. However, okay, looking again at the criteria, array elements being written, yes. Can the elements be written by more than one loop iteration? The answer is we don't know, because the array element is indexed indirectly through an index array indexed by the I here. So we do not know if more than one iteration can read or can write these particular index of produced by index of I. And also we do not know, since we do not know the index, we don't know which iteration will read, which iteration will write elements here. So no, we cannot parallelize this with good conscience, because we don't know if there are loop carried or other kinds of dependencies. Talking about other kinds of dependencies, data dependencies, true data dependencies, are not the only kind of dependence. We also have two other kinds, which are called anti-dependencies, exemplified here with the case when you read the sum variable here and then you store the sum variable here. So there is a dependence here. We cannot reorder these statements because the third statement here, the third line here, will store a value which is read previously. This is write after read, or an anti-dependence. This is a false dependence because it does not carry any data. So it can easily be removed by rewriting with variable renaming. So rename the second sum to sum2. We preserve the data, the true data dependence here, but we have broken the anti-dependence, which means that these two pairs of statements can be reordered any way you like, and in particular they can be executed in parallel, which is what we want to achieve here. Same example, but different kind of dependence here. We have a write after write, or an output dependence between the two storing to sum variables. It's similar to the anti-dependence, but the reason for not being able to reorder or execute them is different. The way to remove this kind of dependence is exactly the same as before. We rewrite with a new name, and then there we have it. These two pairs of statements are again parallel, and you can execute them in different order. Let's see how we can sort of spot this kind of dependence and find out in loops. All right, here's a more complicated loop than what we looked at before. So where are the dependencies and how can we remove them? Well, first of all, we have a loop carry dependence on, we have an output dependence on X here. Actually, we have both anti and output dependencies on X here, because we read and write this element. There is true data dependence inside the loop body. That's not a big deal. Let's see here. I'm going to remove this. But there is a the output dependence between iterations. So how can we remove that dependence? So then we have also a dependence between an anti-dependence here between loop iteration I plus 1 and I. And how can we get rid of that? Well, when it comes to the X variable, we privatize it, because we only need it, we can have a private copy within each loop iteration. So that is a way, so you could sort of potentially have an array, but the easier way is to do it with OpenMP. So we parallelize this loop with privatized X, and then we have gotten rid of this kind of dependence. So we rename the X to be private for each thread, and then we're done. The other kind of renaming we do is that we take the A of I plus 1 and put it in a array of its own. So we rename it and we give it a new name and a new storage place, and then we use that in the loop. And now this loop can be parallelized. This actually renaming is also possible to do in parallel because just a copying of an array. So here we see in order to get this loop parallel, we had to add some extra space. We had to allocate a new array A2. We also had to do some extra data movement to be able to make the second loop parallel. Is this worthwhile doing? Well, it depends on how big the array is and how much time this kind of calculation done here is, if it's worthwhile. But this is a case that you always have to sort of consider. There's a trade-off between space and extra computation and extra data movement to trade off against parallelism. And whether or not it's worthwhile depends on your for loop. Here is another kind of for loop and which has dependencies, and how can we get rid of those? Well, there is a dependence here in the D1 because every loop you store it. Now this is actually a stupid kind of dependence because this is just a repeated storing of the same thing, and the only thing you have to consider is to make sure that you get the last value of X here. And there is also that's actually the only sort of important dependence here. It's easy to get rid of in this case. You move out. Actually, you would have liked to do the same thing. You would have liked to sort of move this statement out here, just writing D1 equals 2 times X. Now, this is not so easy to do in a parallel loop. You have to do a little trick here, and the trick is to declare X last private. In OpenMP, last private means that the value of X outside the for loop will be the value of X of the final for loop in the sequential loop, and this is exactly the behavior we'd like to get. Here's a little more trick to it. Here's a for loop which has actually a loop carry data dependence between the iterations. Graphically, it's easier to spot here. We see here that the storing of array B here takes an element from the previous iteration. So within an iteration, you can't really sort of say it's parallel because there are iterations are not independent. You have to have the value from the previous iteration. This is actually easily fixable if you can sort of do this kind of skewing like shown here. What you want to do is that you want to calculate the B of I minus 1 before you start the for loop, and then you make a new for loop where you have this kind of dependence instead. You produce a data value to I plus 1, and then you have the same kind of behavior between C and A as before. And this is how you write this. You have to move the storing of the first sort of B element before the for loop. You do one iteration less than before, then you reorder the iterations or the statements inside the for loop so that you produce the A element first and then the B element. You could have kept the ordering, but then you would have needed to change this one to C of I, which is okay. And then you have to add the final iterations storing of A as before. This is called software pipelining, and this is a very useful technique to get rid of some of loop carry dependencies. But unfortunately, not all loops can be made parallel, and then you have to do more significant restructuring of your code, or live with the fact that loops cannot be made parallel. So we have now finished this module. It's now time to go to the course website and follow instructions on how to do the quiz It's a simple quiz and a few questions to answer about this particular module. Thank you.